Hi guys, welcome to Mr. AP. This is Mr. T and I'll be going through the 2024 AP Chemistry free response questions. This was a very long and tedious AP Chemistry FRQ, so let's get right into it. So first is our periodic table, and then this is our formula sheet. So basically the first question is asking which hydrogen atom most readily participates in the chemical reaction. So this is going to be the hydrogen at the end of the hydroxide, so the one attached to the oxygen, so it would be this one right here. And then the next question, student begins the experiment by dissolving 10.22 grams of sodium hydroxide in a 500 milliliter solution. Calculate the molarity. So we know molarity equals moles over liters. So to calculate the moles, we have 10.22 over 40, and then times the liters, or 1 over liters. So you convert milliliters to liters, would be 0.500, and then 22 divided by 40, 0.5, which gives us 0.511. So three significant figures, so 0.511 mole. And then question C, it's asking for the pKa of lactic acid. So we know at the half equivalence point, the pH is equal to the pKa. The equivalence point is at 16 ml. So half of that is 8, and that's about 3.9. And remember, for significant figures, you do one after the graph, one after what the graph notates. So here it would be 3.9. And then after it asks where basically this situation would be in this titration curve and draw an X. So basically we know we can find this using the Henderson-Hasselbalch equation. We know the pKa of lactic acid. So basically the pH would be pKa minus the ratio of the base over the acid, or plus the log of the ratio of the base over the acid, which is 1.2. So I put this in my calculator. That will give us about 3.6. So the pH equal 3.6, and we can see at 3.6 is about 6 ml. So that's where the X would go. And then here it's asking if you double the concentration of NaOH, what will happen to the titration curve? Basically, if you double the concentration, it'll take half the volume. So you'd start around the same initial pH. Once you come to 8, it would shoot up, and then it would curve back like that. And then lastly, or not lastly, but part E. Alright, so part E, they're asking how much heat was produced in this reaction. So give us the moles of lactic acid and the moles of NaOH, as well as the volume. So to find this, we take the molarity and multiply it by the volume of 0.5 moles of both times 0.1 to get 0.5 times 0.1, which would give us 0.05 moles. And then we just convert these moles into grams. So we know that NaOH is 40, so you do times 40, and then 0.05 times 90, which is lactic acid. So that would equal 2, and that would equal 4.5. 2 plus 4.5 equals 6.5 grams. So we have 6.5 grams, and we know the equation is Q equals mc delta T. So now we find our mass. We have 6.5. Our C is 4.2. And then lastly, our change in temperature would be 3.4, or 3.2, sorry. 6.5 times 4.2. So that would give us, so since we have 2 sig figs for this, we would have 87 joules. And then for this question, you just take your joules, convert them to kilojoules, and then divide it by the moles used. So we use 0.05 moles. So I'll give you 0.05 0.74 kilojoules. And then basically this one would be disagree, because just because the heat is being lost in the surrounding doesn't mean that the reaction is producing less heat or enthalpy. The second FRQ is asking that 0.0114 moles of CO2 was produced after the reaction goes to completion. Calculate the number of grams of CO2 produced. So to find grams, just do moles times the molar mass. Sorry. Yeah, you take the amount of moles times the molar mass. So carbon is 12 plus 32 for the two oxygens, 0.0114 times 44, and that gives us 0.502 grams produced. And to calculate the volume, we use ideal gas, so PV equals nRT for temperature. So we have our pressure is 1.25, volume's unknown, moles are given 0.0114. Our R would be 0.08206, and then our T is 20 degrees Celsius, so you'd add 273 to 20 to give you the Kelvin, 293. So to get volume, you do 0.114 times 0.08206 times 293 divided by 1.25, and that would give you 0.22 liters. Or sorry, 0.119 liters for sig figs. And then if the surface area or reactants so basically the surface area will increase if it's grinded into powder, right? And the rate determining step for the overall reaction is the dissolving of the solids. Would the time required for the dissolving of the solids in the second experiment be longer, shorter, or the same? This would be shorter, because if there's more surface area, there's more space or more places for the molecules to collide. Therefore, there would be a shorter time of reaction. And then the volume will be the same because you're not changing PV, or you're not changing P and R or T, so the volume would be the same because it's an identical experiment. And the limiting reactant here, so we have trial 3. So we have this number of grams of H2C4H2O4, and then this amount of grams for NaHCO3. First, you'd find the molar mass of each. So for the first compound, it would be 2 plus 48 plus 2 plus 16 times 4, which would give us 116. And then for NaCO3, the Na's molar mass is 23, H's is 1, C is 12, O is 3. Yeah, give us 84. So you divide, and then divide. So that would give us 0.0133, and then that would give us 0.01489 about. But we're not done here yet, because in the reaction it says 2 NaHCO3s per each of the H2C4 H2O4s. So you'd have to multiply this by 2, and that would be greater than this. So therefore, because 2 times the amount of NaHCO3 are consumed, so therefore NaHCO3 would be our limiting reactant. And then the reaction value is greater than 0 explain why the entropy increases as the reaction progresses. So basically, since there's more molecules in general, after the reaction there'd be more entropy because there's more like variations of the molecules, which would increase disorder. And then for E, so we know that delta S is positive and it's endothermic. So delta S is positive, it's endothermic. So if it's endothermic, that means heat is going in. Therefore, it would um, it would be positive delta H. So since they're both positive, it's only thermodynamically favored at high temperatures. Therefore, it is not thermodynamically favored at all temperatures. This one, we know P equals negative log. You just take the negative log of Ka2 and you get your answer. And then it's asking for the pH of 7. So we have 7 as our pH. And then set that equal, um, what's it called? Set that equal to the Ka of the one you just found. So negative log of 8.5 times 10 to the negative 7. So that'll give you about 6.07-ish. So 6.1 with sig figs plus log of the ratio. So we'll just say x, which is our ratio. So 7 minus the pKa, which is 6.07. And then you do 10 raised to whatever number you got. And then you get about 8.5 if you use this number, or if you use sig figs back here, you get 7.9. So, is asking what sterling silver is an alloy. That's not other metals, such as copper by mass. The alloy can form retardant of AgS2 when it reacts with hydrogen sulfide. Ask me the oxidation numbers of silver. So as a solid, silver has a 0 as its oxidation number, but then sulfur is -2, Ag would have, there's 2 Ag, so it would be +1 for each. So the oxidation number for Ag and Ag2S would be +1. And then sterling silver is better classified as a substitutional alloy than an interstitial alloy because basically the radius of silver and copper are very similar. So instead of the copper being in between the silver atoms, that would be replacing or substituting the silver atoms in the alloy. And then basically silver has a larger atomic radius because of electron shielding. Since it has one more valence electron ring than copper, the previous valence electron ring will be pushing it out even though silver has a higher effective nuclear charge. For this question, they're just asking what's the moles of silver atoms removed. So first you find the how much Ag2S was actually removed. The 409.21 minus 398.94. That'll give us 10.27 grams of Ag2S. So this is our molar mass. So we would have 10.27 divided by 247.8. And then now we'll have to find the percent mass of Ag in Ag2S. So the percent mass of Ag in Ag2S, you take the molar mass of Ag, which is 108, 108, which is rounding, times 2, divided by that molar mass. So that'll give you around 87%. So you take that molar mass and divide it by, or multiply it by 0.87, and then multiply that answer by 2, and you would get about 0.07. Yeah, 0.0723 moles of Ag atoms. So for this question is electroplating deposit is solid rhodium. So our our product is RH solid. So this would be our cathode, our redox reaction, plus the 3 electrons, give us a solid, then O2, 4H plus, 4E minus, which will give us 2H2O. So this one will have to be flipped and multiplied by 3, and this one will just be multiplied by 4, so we'll just change that. And basically, we would get 4RH3 plus aqueous plus 6H2O plus 12 electrons, which would yield 4RH solid plus 3O2 plus 12 hydrogens plus 12 electrons, and the electrons on both sides would cancel out, and then this yields this in our final reaction. And then our E cell value would just be 0.8 minus 1.23, should be negative 0.43. And this process requires a use of external power source because the voltage produced from the cathode is less, or the voltage taken from the anode is less than the voltage produced from the cathode, so it would have a negative E cell value, which means it requires an external power. And then it's asking for the length of time in seconds required to plate 2.8 grams of RH onto a sterling silver. So you just convert 2.8 grams to the moles of RH, and RH is 102.91. And we know the electron for each mole of RH is 3 moles of electrons, and each mole of electron, it was like 96,485 coulombs. Hold on. Yeah, for Faraday's constant, we get C, and then it gives us 2C per second, so you cancel out all of your thingies, and then yeah, you get 2.8 times 3 times 96485, and then you divide that by 102.91, and then divide that by 2, so you should get 3,900 seconds. Then basically this one's asking what is the highest temperature of the water recorded. So this would be about 38.5, and you would record to the decimal value after what the visual recordings or the lines are on the graph. And this one's saying how does the speed of each of the molecules change after the metal cube is added. We know the metal cube has heat to it, so this would be, it'll just be longer. And the metal transfers this much energy, calculate the specific heat of metal. So you'd have this equals the mass, which is 981, 98.1 times the specific heat capacity, or specific heat capacity times delta T. So our delta T was 100, and so 38.5 is the highest temperature, so we have 100 minus 38.5, so the metal changed by 61 degrees. The metal changed by 61.5 degrees, So our delta T would be 61.5. So we have 2940 divided by 98.1 divided by 61.5, which would give you 0.487. Basically, part D is asking how the mysterious metal compares with the aluminum in terms of temperature change. Since that metal had a 0.487 heat capacitance and aluminum has a higher one, the temperature change of that metal would be higher than the aluminum. So this is just asking for the expression for the equilibrium constant. Kc would be Hi, and then that'll be squared over H2 times I2. So this would be squared because it forms two products. And basically it's asking that the Q is 0.67, and this is the following particular diagram is incomplete. So we have a 0.67 equals 2 and 2. So we have 4 here, and then we have Hi squared, sorry, not square rooted. And then we get 0.67 times 4, you get 2. Or sorry, you have 3 times 2, sorry, so you have 6. You would have 6 times 0.67, which would give you 4. So about 4. Why do I keep writing square root sign? Squared. Hi squared. And then you square root the 4, and you get 2 Hi's. So you just draw 2 of them. Like, and then make sure you colored in the iodine. Like something like that. And this is asking what could have increased the moles of Hi, and the student did not add more Hi to the system. So as we can see, the enthalpy is negative, so that means it's exothermic. That means heat is a product. So if you lower the heat, it will shift right towards the product side, thus creating more Hi. So this was just lowering temp. And after the equilibrium is established, the mixture is transferred to a larger container at a constant temperature. As a result, will the number of Hi increase, decrease, or remain the same? So I put it would remain the same because if it was in a larger container, the pressure would decrease to cancel out the moles when increase or decrease. And also here there's 2 moles on this side and 2 moles on that side, so adding pressure won't really shift the reaction in any way. So question 6. So basically for A, it's second order because a graph of 1 over NO2 is linear, so second order. For this one, it's saying the disappearance of NO2 is this was the appearance of O2. So there's a disappearance of 2 NO2 per appearance of O2. You just take that number and divide it by 2. You get 6.52 times 10 negative 7 divided by 2. So that'll give you 3.26 times 10 to the negative 7. For this, I think it would just be a double bonded oxygen to the nitrogen, something like that. And then would the bond angles be different? Yes, they would be different because one has a lone pair, the other doesn't. So this would be linear, and this would be bent. So the bond angles would be different as linear is 180. And yeah, so you would agree with the student. Agree. Next is asking the mass of the solid NaCl needed to prepare the 100 milliliters of the 0.34 moles. So you take the moles times 0.1, or you take the molarity times the volume to give you the moles, sorry. So that'll give you 0.034. So then you take the moles and multiply it by the molar mass. That'll give you 1.986. And then you do 3 sig figs, so that'll be 1.99 grams. This one was interesting, the procedure. So basically, in between scooping the paper and destroying the mixture to dissolve the NaCl, you'd have to take a beaker, and then pour distilled water into it. And then you would put the NaCl into the beaker. And after that, you swirl it. And then the fifth step is to invert the mixture several times. So what you need to do is you'd have to have a volumetric flask. And basically with the volumetric flask, you would mix it. I'm not too sure about this question, but I'm pretty sure that's along the lines of it. And lastly, it's asking for basically the student does this chromatography, and the paper, instead of moving for 30 minutes, they let it move for 15 minutes. And is the gap greater than, less than, or equal to? So the gap would be